Okay, so we have our Lagrangian as a function of all our QIs, QI dots, and time. And how do we go about forming our Hamiltonian? Yes.
Using the Legendre transformation?
Yes, so we're going to use a Legendre transformation. A Legendre
No.
transformation. So we define PI. So this is a Legendre transformation. What do we want to do? We want to get rid of the Q. We want to get rid of our QI dot. And so how do we define this then?
Partial L respect to Q dot.
Respect to QI dot. Like this. And how many are there of these?
N.
Yeah, as many as there are generalized coordinates. So we're going to say our H. And what do we want to do with our H? We want our H to be a function of our QIs here. I mean, our QI here. And then we want, in terms of our new variable, and possibly time. And so to do that, we do the Legendre transformation. And how does this go? We take the variable we want to get rid of, which is QI dot. We multiply that by the variable we want. And since there's a whole bunch of these, we have to sum over all possibilities here. That minus our regional function. The claim is that that results in a function that only depends on the Q's, the P's, and possibly T. That makes sense? So how do we prove that? So this is formula, this will always work to calculate a Hamiltonian, because this is really what it is. Now, in many cases, almost all the ones we're going to be dealing with in real life, this reduces to
T plus
V. Okay, and anything you're dealing with in quantum mechanics is always your T plus V. So, but this is what it normally is here. So let's go through and actually do this. So what do? We look at the exact differential, or DH. And our DH is what?
Partial H respect to QI.
I mean, this guy. Oh, you are doing that. Okay, never mind. Oh yeah, no, you're not that. Okay, so no.
Oh, just two.
Okay. So let's start with this guy.
PI partial.
Okay, so I have dpi dot pi.
Yes.
Minus
Plus
Plus
UI dot DPI
QI dot dpi
minus 3L.
minus your DL. Okay, and I need to save a little bit of time here. Let's actually put more DL here, but you're right. DL using this becomes
Partial L respect to QI.
and I need a sum. Someone I should sum partial here. L respect to QI DQI.
Plus partial L respect to UI dot
Dot dot.
plus partial L respect to T.
Yeah, so this is a piece on some I really don't want about that line there. Better. And then we'll have then this, I'll put a minus sign here because it's coming with the minus sign here. This partial L with respect to T dt. And what do we do with this?
That
This one here.
PI.
Yeah, this term here is our PI. And so that term here cancels because it comes with the minus sign here, cancels this term here. Oh, does not cancel that term at all. Cancels that term here. And so what we're left with is that this DH here depends on our DPI, or DQI, and then DT. And that's actually shows the functional form. Does that make sense? And then we finished it off. We said that what? Now we can say that our DH is also somewhat I go from 1 to n, and then how does that one go? Now using this one here, that DH is
Partial H respect to QI.
partial H respect to QI, DQI plus
Partial H respect to QI.
PI, DPI plus lunar. We can do that. And we know that differentials are unique, so there's only one way you can write them. So that means that anything in front of this DQI here. That has to be the same, and what do we do with our buddy here? We had another way of writing that. Yep.
Yeah.
PI dot.
Yeah.
We know that this is equal to d by dt. Partial L with respect to Q I dot here by Rogers equations. This is nothing but our PI dot. So we can equate those two here, and that gives us our PI dot. Minus sign, here's my body here. And then what else? I can take this one here. Wait it for this one here. And that gives us our QI dot, this partial H, respect to PI. And these are really what are being called Hamilton's equations. Here, but then we can do the last one here as well, which technically we're under two, but no one worries about this one. This is partial of H with respect to T. Was minus partial L with respect to T. Let's see if I'm still on the board, whether this is legible, and all these statements are true. I think this one no. It's awesome. Does that make sense? Now, what order equations are those? First order, but how many are there?
2n.
2n, because we have n for these and n for these. Okay, so that's what we have. So wanted to actually go through and actually do an example. So we took our standard case of our spring. So let's do our spring. We can say apply spring. So what are we gonna have? We start off with, so let's run the picture. Right, this is our n equals 0 line. This is x. This is k. This is m. So last time we said our kinetic or Lagrangian is always t minus v. So this is 1/2 m stop squared minus 1/2 k x squared. We calculated our p of px. This is partial L with respect to x dot. And this is your m stop. And then we wanted to construct in the Hamiltonian, so we go back to the original expression of it. So H is by definition sum of I of these Q by dots, PI minus L. And in our case here, how many terms in the sum? One. Just one. So this gives us what? This gives us x dot px minus L. Now what do you have to do? We have to rewrite this all in terms of
Yes.
the px and x, because what does your h depend on by definition? The q's and the p's. You can't leave any x dots. You can't leave any q dots in there. If you do it, it's fundamentally wrong. Again, it helps if I wish I had a videotape of one of the professors. I could record it for you, so you can see what happens when somebody goes ballistic on a point, and then it turns out that you end up remembering it for the rest of your life. Yes. Okay. Well, all of his problems, and there were many. He was the only one that truly, that was the first time I actually formally understood what was going on with Lagrange's equations. He was the first one that actually kind of made it clear. With all of his problems, they were legion. That was one of them. He also picked his nose during class and scratched himself. And you realize the difficulty, how distracting that is if somebody goes like this and starts picking their nose, and then starts scratching themselves. That's remarkably distracting. Okay, and he wouldn't complete his sentences. So he started off and he had this really strong accent. Okay, see the Lagrangian is T. Okay, but the exam will be on Tuesday. Okay, so if we go back over here, we have H. That's very hard to follow. That's very hard. But I digress. So our x dot is
px over n.
yeah. So we saw this for our x dot. This is px of m. So this is our px over m. Here, minus, and then we put in our buddy here. So this is going to be our 1/2 m. Our x dot comes in squared. And minus 1/2 px. Like that. So this gives us our h equals px squared over m. I'll put this down here. This is minus px squared over 2m. And then plus 1/2 k x squared. And we set this from here. Goes to our px squared 2m plus 1/2 k x squared. Boom. So that is actually what your kinetic energy is going to be. I mean, what your Hamilton is going to be. It's your kinetic, and your kinetic is your p squared over 2m. Why in classical mechanics do we know that kinetic energy is p squared over 2m? The 125. Give me the 125 argument for why kinetic energy is p squared over 2m.
Multiply by m over n.
Yeah. So we know that from, that's kinetic energy. So if you multiply top and bottom here by m, this gives me mv quantity squared over 2. This is just p squared over 2. So this is your kinetic energy here, this is your T, and this is your potential energy. And so this will very frequently, I'll give you the condition of when it will work. Hamiltonian, for almost all practical purposes, will always mirror T plus V. But just always keep in your head that formally it is this. That's formally what Hamiltonian is. And it just so happens that in a very large number of cases, it reduces to simply T plus V. That makes sense? Good. I thought you were going to say something. Questions? Okay. So now let's get the equations motion. And again, just like before, remember when you do a Hamiltonian, when you do a Lagrangian on a simple problem, not really anything to write home about. There's a lot more work. I think I could have gotten that answer a lot easier. The same thing's going to happen here. Except it's going to have a more dramatic effect of all you kidding. Okay. But that's just the nature of taking a sophisticated idea and applying it to a simple problem. Okay, so let's get the equations of motion. So what are our equations of motion? We have q dot equals a partial of h respect to pi. That's one of them. And then we have minus pi dot equals your partial of h respect to qi. So what do we have here? We're going to have x dot equals a partial of h with respect to px. And then this equation here will then give us minus px dot equals a partial of h respect to x. Okay. Be prepared to be remarkably unimpressed. Okay. If here's my h, what is a partial of h with respect to px?
Px over n.
Px over m. Okay, why is that remarkably unprofound? We already had this from the definition of px. We got exactly the same thing we started with. Ooh, cool. Okay, again, don't be, I said, prepared to be underwhelmed by this. Now let's do this one. So this gives us minus px dot equals. What is the partial of h with respect to x?
Over Oh, that's a little less.
Yeah.
On x,
So this is
kx.
just kx. So this is kx. Let's write it like this. Again, you can say, really? Okay, what is that? Give you a better name for this equation? Give me two different names for this equation. Both from 125.
Forces.
What's the force of the string called?
Hooke's law.
Hooke's law. So yeah, Hooke's law here. Okay. Ooh. Okay. And what do you know about the time derivative of momentum? That's nothing but,
And then,
that's your mass, right? MA. So you can either say that this is just Newton's second law, or you can say that this is Hooke's law, it doesn't matter. But again, nothing overly profound. Now, how are you gonna have to go about solving this? You have to solve this for px. And where would you put it? Into here. What do you get? You get then mx dot equals minus kx. So this is just mx double dot equals here. Yeah, F equals m. So you could solve the string problem, but this is basically, you know, using a howitzer to solve the string problem. This is beyond overkill. Okay. Any thoughts? Questions? Okay, let's do another example, and then we'll talk about more general properties of the Hamilton. Now, okay, so this is fair for U3. Okay. So for U3, okay, you two will get it soon. No, 3, 4, because you were there as well. Okay, sorry, everyone but you, Molly. Okay. And Kat and David, because they would all be in that category. So you, Molly. Okay. With the exception of Molly. Why does this become important? So when you do quantum mechanics, what do you have to deal with?
Hamiltonian.
You have to write the classical Hamiltonian for a problem, and then what do you do to make it quantum mechanical? You replace, yeah.
You put a hat on everything, right?
Sure, okay, why do you put a hat on everything?
You
Because all the
bring them
quantities
into
become-
their quantum mechanical forms where they're time dependent.
Okay. They become operators that act on a wave function.
Yeah.
So your px and your x and stuff like this, they all become operators, and then they act on a wave function. But your first step is writing the classical expression. Okay, so from a practical point of view, it's indispensable. You can't do quantum mechanics with this. Okay, now you could ask, why on earth does that give you rise to quantum mechanics? No one knows. Okay, that's just one of the postulates. We know that works. Well, exactly what's going on with the postulates, that's no one understood that. Okay, now does that mean there's something more profound? I suspect so. There's always something more profound. Okay. Just so you know, okay, if you come up with a brand new profound theory, at least make sure it's based on something. Okay. 2 years ago, there's a student, I won't mention the student, actually it's no longer good. Who basically came up with a whole new theory that was going to explain space, time, and everything else, and they always end up coming to me. And so he had this extremely long presentation, and his insight was basically what momentum was. And when he's presenting it, the momentum is this, and I was supposed to go, oh, you solved everything. It's just utter nonsense. And he showed me all these things, and he had no idea what he was doing. Okay, I'm not judging. I'm just saying it did not help his case that when he put up his laptop, there was a giant picture of a marijuana. That's just say that did not necessarily bolster my confidence in his brand new shiny theory. But at least, if you're going to come up with a brand new shiny theory, at least, understand the basic physics of what there is. You can't start redefining all your new terms and saying, well, I think momentum is really this sometimes, except when it doesn't do it. I've had more than one conversation over the years with people. What's condemning it? Okay, questions of that? Let's do another example. Let's do the spherical pendulum. Okay, sometimes called conical. Anyway. What is that? So if my hand is the bob here, and if my arm is the length, was a conical pendulum. I mean, one that can basically just kind of go anywhere like this. Okay. That's gonna be a conical pendulum. So let's actually figure out the Hamiltonian. What is the Hamiltonian? For a spherical pendulum. At the start, we need to write,
Lagrangian.
we need to write full Lagrangian. So we first need to go full Lagrangian. And you tell me how you get down. Close.
So what kind of coordinates are we?
That's a great thing. What kind of coordinates are we using?
Would we use a theta 1 this way and a theta 2 this way?
That's exactly what we're gonna, it's not gonna be, theta 1, yes. Don't call it theta 1, give it a better name. Okay, more familiar name that everyone knows.
B.
Because we're gonna use spherical
Spherical.
coordinates for this, okay? So we're gonna use spherical coordinates. So what we're gonna do is we're gonna write L in terms of spherical. Okay. So let's do a little overview of our spherical coordinates here. Okay, this is R. What are our other spherical coordinates?
From Z to R.
From here to here, that'll be theta. That's always theta. If you're in math, it's always phi. Phi and phi are the same thing. One's English, one's Greek. Okay, then how do we get phi?
Perpendicular down.
We drop, imagine light shining on here, and it's casting a shadow of R on the XY plane. So here's our shadow. From here to here is our phi. Make sense? Then how are these things given by? It's getting a little cluttered. If I would say draw X and draw Y and draw Z on here, what would you do?
Yeah.
You drop your little perpendicular here, like this. So this is perpendicular. So this is Z. So what does Z equal? R cosine theta. And this right here is our R sine theta. That means this is R sine theta. How do I get my X and phi? I come here. And you drop a perpendicular. That's a perpendicular here. So this distance here is X. This distance here is Y, but Y also can go back here. Maybe this is also Y. Okay, so how do we find them? Y is going to be what?
R sine theta sine phi.
And then our X is,
R sine theta cosine phi.
yeah, so this is going to be R sine theta cosine phi. Should be consistent, right? Speaking of going, people asking weird things. When I was in South Carolina where I met my wife, I was so happy I was there. But a woman called me on the phone and she was selling this little, it looked like a baby's teething ring. And if you put this baby's teething ring in the washing machine, you never had to use detergent again. It was going to take care of everything. She was having a hard time trying to explain the physics of what was going on with her, and she gave me a website. And honestly, I was going into the phases of the moon and stuff like this. And crystallized water. Oh, it was crystallized ice. And she wanted me to explain the physics of this for her. And that was a little challenging. See, well, there isn't any physics. I think this is fraud. You might want to be careful selling this. It's also a news report by a news report on that because that was making news going all over the town. So that's what happens. We used to keep a file of them here in the physics department on just crank things we got. Because we would get a lot of cranks, so we may help them file them. You might still have it, you may have it. Somebody wrote a book. He was obviously going insane because he had diagrams that were incoherent. That explained his theory of it's always relativity and quantum mechanics and it's a hobby. Okay, so what are we doing? Everyone happy with this? So, what are we going to have then for a little conical pendulum? Basically, going to have the same idea. Does that make sense? Except for R is going to be
The length of the.
will be the L, and the length will be fixed. That makes sense. So in our case, oh, and then the Z will be negative. Okay. So in our case, conical. No. Okay. We have X equals L sine of theta plus phi. Y equals L sine of theta sine of phi. And Z equals minus L cosine of theta. And what we're going to do there is that we'll have we're going to call this angle here. We're going to make that theta. But it's the same idea. Make sense? So let's direct the kinetic energy. Kinetic energy is 1/2 mv squared. Now, how can I write that kinetic energy then? What can I say about v squared? Again, when you write the v squared, how do you always write it?
Cartesian first.
Always start with these things in Cartesian. And always make certain you have a fixed orbit. In this case, the fixed. This is just going to be origin. So this is going to be what? This is going to become x dot squared, y dot squared, z dot squared. Which means we need x dot, y dot, z dot. So tell me about x dot.
L.
L.
Cosine theta.
Cosine theta. L cosine theta.
Theta dot.
Theta dot. Cosine phi. Plus
L sine.
L sine
Theta dot.
theta.
Theta. No, it should be a minus.
Minus
Minus sine phi.
sine phi
Theta.
phi dot. Y dot becomes our L theta dot. Cosine theta. Sine phi. Followed by
L. Theta.
L
Theta.
y dot
Sine theta.
sine theta
Cosine phi.
cosine phi. Z dot
Minus Oh. Plus L,
plus L,
by add up theta dot,
theta dot,
sine theta.
sine theta. Okay, we have to square all this and then do some stuff. So what do we get? Well, actually, what do we get? We get our, so if we look at x dot squared, plus y dot squared, z dot squared. We end up with L theta dot cosine of theta and phi minus L y dot sine of theta sine phi, that don't all goes in squared. Plus, I thought theta squared. Z squared. Okay, so this equals what? Let's say with this term here is going to be squared, so this will become L squared, theta dot squared, cosine squared theta, cosine squared phi. I get my body here squared. Then I'm going to get twice across them. That's my x dot squared. Does that make sense? Good. Now let's do the same for the next term. Next term, L squared, theta dot squared, cosine squared of theta, sine squared phi, plus L squared, phi dot squared, sine squared theta, cosine squared phi. And plus twice across here, plus 2L squared, theta dot, phi dot, sine of theta, cosine of theta, sine of phi, cosine of phi. Then my buddy here. Plus L squared, theta dot squared, sine squared of theta. What great thing happens? A lot of great
By factor something.
things.
Yeah, so.
Which ones cancel? Yeah, this is great, because this is having a lot of like weird mixed terms that they cancel. Okay. Now what can I do with these terms here? And then these terms here.
Factor
L A.
L squared.
Yes, I'm following L squared theta dot squared
Cosine squared theta.
cosine squared theta. Then that leaves me then with
Cosine
sine squared phi
plus
cosine squared phi. Hey, does that have another name? That's more. Then I can do this fellow here, L squared, phi dot squared. I can call it the sine squared theta. That leaves me sine squared phi. It's cosine squared phi. Hey, I think that has an eliminating two. Let's call it one for no other reason. Now we have in the other fellow. Plus L squared, theta dot squared, sine squared theta. I think we have one more nice thing we can do.
Got it. L squared theta dot.
Now you take this term, combine it with this term here. This will give me Well, L squared, theta dot squared, cosine squared of theta, sine squared of theta. That equals to 1. And we have the L squared, dot squared, sine squared theta. So what are we left with? We are left with
There's a plus sign.
well, I have no idea what the equal sign there. Thank you. Keep notes. So this is L squared times theta dot squared plus L squared y dot squared sine squared theta. And if you look at that, there's a part of you who would want to say, duh, why didn't you just write that from the get-go? Why would you actually have guessed that if you stopped to think about it? But why did those pieces make perfect sense?
There's two in this momentum.
So here's my L, here's my theta, and here's my phi. It's gonna be easier for me to do it this way. What is gonna be L theta dot quantity squared?
Like R omega.
That's R omega, isn't it? That's just R omega this way, right? That makes sense. But why is this R omega too?
The L sine of theta is
Is-
R.
Is this R here, right? And then you have the omega here, the phi dot. So this is just, you know, R omega in the theta direction, and this is just R omega in the phi direction. Not too surprising that they just independently come out square. That makes sense? This is like I'll say, it was R omega, where this is gonna be L theta dot. And this guy here, this is like it equals R omega, where this R here is gonna be this radius here. Sine theta. And then my angle this way. It's my job. Does that make sense? Okay, well, that said, let's actually construct our Hamiltonian. I'm sorry, our Lagrangian. For L, which is T minus V, is gonna be our 1 M. Now V squared is going up here. So this is my T. And minus, now what's my potential energy? There's only one. So it's MGH. We have MG, and what's our H? It's that minus L cosine theta. Okay. So what are we left with here? We have our L. Is 1/2 ml squared. Theta dot squared. Plus phi dot squared. Sine squared of theta. Plus MGL cosine theta. Now you tell me how to find the Hamiltonian.
We have to do what John should have.
Yes, so we need the what? We need our PIs, which are generalized momentums. How many generalized momentums do I have? 2. We're gonna have one for theta and one for phi. So we have two P's. Okay, we'll call one P theta. And this is gonna be the partial L with respect to theta dot. What does that equal? This is
ML squared theta.
M also theta dot. We're gonna have P phi. Which is a partial L with respect to phi dot. And that's my buddy.
ML squared phi dot sine squared.
Yeah, it looks weird, but that's what it is. This is M L squared phi dot sine squared theta. So what do? We're gonna solve this for theta dot. So our theta dot, this is P theta for ML squared. And solve this for phi dot. So this is gonna be P phi over M L squared sine squared phi. Then we can construct the Hamiltonian. So our Hamiltonian is where H is the sum on I of Pi Qi dot minus L. So what does this give me? This would be theta dot P theta plus phi dot P phi minus L. That makes sense? Now, what do we have to do with all the Q dots? We have to get rid of them. That makes sense? Let's get rid of them. So I have my body theta dot up here, so this is P theta times ML squared. Make that look for such. Okay, times P theta. Plus what? My P phi, my phi dot, my P phi over ML squared sine squared phi P phi minus my Lagrangian. My Lagrangian is this, but I have to get rid of my theta dots and phi dots here. This is going to become my 1/2 M L squared. My phi dot is up here. This is my P theta over M L squared plus my phi dot, which is P phi M L squared sine squared phi squared sine squared phi. And then minus the term here, my minus MGL goes into that.
Shouldn't be sine squared theta.
Oh, where?
Somewhat, maybe
Where?
maybe all of the sine squareds. Like right there, where you solve for phi dot.
Okay, so, oh, you mean this should be a theta here? Yeah, okay, I had father. I'm gonna start screwed up. I have father because I know it wasn't important today. To be honest. Well. Sorry about that. Let me know when you have that. Thanks. I think I'm good now, right? Let me know when you have that done. At least want to put these together before the call quits. Okay, now, what do you think the most common mistake is when I ask people to do these things? I get this, what don't I get next? Simplify it, just don't leave it like that. Yeah, that technically that's correct. But it's stupid, don't obviously work it out. What happens here? This term here and this term here, what is that going to do? That term, if I look at those two terms, I'm going to get P theta squared over M L squared here. But if I look at this term over here, one of the ML squareds go out, and this term gives me minus P theta squared over 2 ML squared. And then what do I get? I get my W here. P phi squared, ML squared, sine squared phi. Then what do? I get in this term here, and again, one of my sine squareds cancel, and then one of my ML squareds cancel. So this gives me minus P phi squared over 2 ML squared sine squared theta. And then so my potential action. And again, don't leave it like that, finish it off. Group these terms together. Through H is P theta squared. Over 2 ML squared. And then what happens here? This term, oh, you should already, no, don't know. This term here in 2/2, so this would mean the P5 squared. Over 2 ML squared. N squared theta. Then minus MGL. Theta. That right here is my Hamiltonian, because it only depends on the Q's and the P's. Does that make sense? So we'll stop here, but we'll finish this up off on Monday. When we finish this off on Monday, how many equations of motion will I have?
2.
Times 2. I can have one. I can have 2 equations with the theta coordinate, and another 2 equations with the phi coordinate. Okay, so we're gonna have 4. We're gonna have 4 equations of motion. Okay, have a good weekend.